All right, good afternoon, everybody. It's a pleasure to be here in the virtual seminar again. I just wanted to introduce briefly 4 topics that are wrapping up, but by way of introduction, my teaching areas are mostly in structural analysis, structural mechanics, and reliability. And overall research areas involve both experimental testing, numerical modeling, and uncertainty quantification, but primarily applied to problems in bridge engineering and using composite materials, so at a totally different scale perhaps to the previous talk. Some of the classical motivations go back to the grand challenges from the MAE, and there are obviously these American Society of Civil Engineering report cards that are released periodically that get into the state of the current infrastructure and the investment needs in order to mitigate or even to offset some of the current deterioration. And some of the research challenges associated with those can be grouped into, novel materials and systems, so that involve both testing and modeling, monitoring and condition assessment, which is understanding better the behavior of systems, and obviously use of technology to perform the assessments. And then decision making and asset management at the larger scale level. So this is improving safety, particularly in the modern era where we're seeing a number of extreme events proliferate. And then again, integrating the economic, environmental, and social impacts at the same time. And something that I've taken a keen interest in the last 6 months or year, and it relates a little bit to our programs, but also some things I've been looking at the national level. And this is very specific, I think, to civil engineering, that the number of graduates that we're producing is nowhere near the needs of the market currently in the United States. And it's a market, I'll show you a slide later, that's predicted to continue to increase in the next decade. So it's an interesting challenge, and I have some thoughts, and again, maybe you have some things to contribute at the end. But quickly, I would like to showcase 4 things that have gone on recently. 3 of them are wrapping up or done already, and the 4th is a kind of a new area. So the first one relates to what's called ultra high performance concrete, which you can see in the center here. It has internal fiber reinforcement. But the idea here is I'm working with some colleagues at UCF to leverage the unique properties rather than going through an emulative set of steps that is common in other research programs. But we would like to use the existing reinforced concrete infrastructure that already exists, in the industry to deploy both precast concrete and cast-in-place solutions. And the specific idea is to use these non-contact lap splices. You can see reinforcing bars here that are internal to a form before the concrete is cast, and notice how they're not in contact. And this is typically a detail that is not allowed under the current code. Or if it is, obviously you have to have sufficient length to transfer force. But here the proposal is specifically to let the lap slip. And this is only possible because of the properties of UCF, UHPC at UCF. And the idea is that you can control the force transfer, you can control the location of damage, and actually you can control the residual capacity as well, as what we found. And there's interesting failure modes. You can see an example here of what happens when these bars pull in opposite directions. It develops this characteristic failure mode. And we've had a full program of small scale all the way through large scale tests and some corresponding inverse modeling that was done to produce the macroscopic interfacial bond slip relationships, which are useful for design purposes and deploying them in situations where the testing had not yet been completed. The second one relates to carbon fiber reinforced polymers used for repair of reinforced concrete structures. And this is something that has been done. It's a very common technique for repair in the field, but the novelty here relates to the use of polyurethane as an impregnating resin as well as an adhesive. And the reason that is interesting is because nobody else other than UCF at the moment has studied this, but you get these very different failure modes. So the one at the bottom here is what happens when you have polyurethane failure, which is purely in the adhesive layer. Whereas if you have epoxy, which is the industry standard at the moment, you actually fail in the concrete cohesive layer, a thin layer at the surface. And currently in the design code or in the practice, it's viewed to be an undesirable failure mode to fail in the adhesive just due to repeatability or what's perceived to be a brittle failure mode. But actually, we've been able to demonstrate with a lot of mechanical testing that the failure modes of polyurethane are extremely uniform and repeatable. And this particular study is looking at the environmental durability of the repairs, because obviously civil engineering infrastructure is continuously subjected to mechanical and environmental loads. So we did an accelerated conditioning battery of tests on these, and we discovered that the chemistry of the polyurethane that's used can actually not only retain failure mode and flexibility and strength, but we can actually improve strength. So here we see approximately 40% loss in strength after a year of conditioning, whereas a more hydrophobic polyurethane is able to resist substantially some of the deterioration due to environmental conditions. So this is sort of an exciting find, and it's something that some industries use, but in terms of structural strengthening, polyurethane hasn't found a strong market niche yet. The third one is really relevant today, as you're all aware, based on some of the news media and unfortunate stories coming out of Syria and Turkey. And actually the photo here on the left I grabbed from CNN, that's a building that was destroyed in eastern Turkey. The one on the right is Northridge in the US. But an interesting thing, and although there hasn't been a lot of damage, or at least reconnaissance related to bridges, bridges are an interesting subject area because they have only what are referred to as dual load paths. So the lateral loads come only through the columns or through the abutments, and therefore they are subject to, or they are more sensitive in their response and the uncertainty to not only the materials, but obviously the systems and how they behave. So it's led to many years of work that I've been involved in formal sensitivity analysis on the nonlinear time history or response history analysis of typical bridges under earthquake excitation. And I'm not sure whether anybody's familiar with formal sensitivity analysis, but it can be done through direct differentiation, or finite difference methods are commonly the most commonly employed, but we developed a hybrid algorithm that takes advantage of both. And the plots that you get out of it, or the products, are this curve that you see an example here, where you find the partial derivative of, for example, the displacement or a response metric with respect to input variables. And obviously you can compare the peak sensitivities between parameters to try and understand what is the most important when it comes to predicting response. And another contribution of this is to take a look at not only the material strengths or the geometry of the system, but also to look at what's referred to as the hysteretic behavior. So this will tell us something about how the materials behave under cyclic load. And it turns out that to be at least as important, or perhaps more important, than some of the more traditional assumed sources of uncertainty in these systems. So there's a lot of things that can be learned in order to prioritize future experimental work, which really in the seismic industry has been focused heavily on columns as the sole lateral load resisting system. So it opens the door for justifying tests, for example, on abutments for bridges. And the last topic, this one is a little bit more esoteric, and it's also fresh, so I put a question mark next to the agencies, and maybe you have some thoughts, but this relates to what I've referred to as user in the loop finite elements. So a colleague of mine and I are proposing, let's say, a paradigm shift in the way that we perform finite element analysis. And the motivations behind this are really the inability to change proprietary code, and even if you have open source code, there's a lot of code duplication that happens, in addition to the need from a research perspective to be able to do multi-physics simulations where you have at least one-way coupling. And a final observation that's maybe a little bit deeper is that they're more fundamental modeling units from which everything else is derived. And this is not commonly done when we try and understand physics-based behaviors. So the implementation is based on what are called parameters. So these are pointers or objects that are associated with different quantities in the finite element domain, and the user can interact with them at the runtime. So you can see a schematic in the upper right here, where a traditional time-dependent analysis is something that the user can manipulate during the analysis, maybe not during the nonlinear iterations, but certainly at the incremental level. And the easiest way to think about it is you could think of it as a superset of user-defined subroutines, right, where you have actually direct access to the methods and the data of the software. So the two examples here quickly, hopefully it makes sense. So here's a set of three cantilever columns where they're separated by these interfaces, and at the interfaces we'd like to represent node-to-node contact or contact friction. And the way that we did it in this particular paper was actually to use linear elastic springs, and the parameters control the modulus of the springs. And through doing that, we can actually develop an algorithm to solve problems of contact friction. So sort of neat. And the second example you can see is some experimental tests that were done on elevated temperature exposure of concrete slabs at Purdue. And we can simulate these using parameters that define the thermal strain and the time or temperature and time dependent behavior of the materials. And I realize it might sound a little bit strange, but the important thing to remember here is these are capabilities that are not inherent in the software. So we're not using thermomechanical enabled elements. We're not using friction or contact detection elements. We're using standard, existing quadrilateral or one-dimensional elements to solve problems that are far more complicated. So it's an interesting thought. It's something that I'm continuing to work on, but it's, let's say, less mature than the other ones. So very quickly, in the near term, there's several things that I'm already working on together with my colleagues here at UCF in the middle bullets here related to disaster resilience, and then also experimental and numerical modeling. As I mentioned before, there's some areas related to education, primarily for civil engineering, that are kind of near and dear to my heart. And I wanted to share this graphic with you. It came from ASEE. And I realize it's a little bit grainy, but I'm not saying civil is the largest sector of the engineering industry by any means, but the numbers are staggering. This is the total number of, let's say, positions, or the size of the workforce, 347,000 projected by 2028, which is a 6% growth. And if you recall, we're not graduating enough as is. So the challenge is, what are the perceived interests of students who are entering engineering, and how do they self-select amongst the majors? And this gap that's developing between research and education and research and industry, particularly in structural engineering, is an interesting one that I'm planning on studying. And then finally, longer term, there's several things you can maybe see the collaboration needs are more social, economic, or experimental in their nature. But as it relates to a topic of interest is the 2070 megacity, which some of you may be familiar with. And I believe that it's our opportunity to go through a major curriculum overhaul and modernization to make, the civil engineer more relevant in the global kind of this integrated context of social, environmental, and engineering. So it's one of the things that I haven't formally started. I can't showcase any publications, but it's something that I'm planning on working on in the medium to long term. So if there's anybody interested, I'd be happy to hear from you. So with that, I'd like to wrap up. Thanks some former students and current collaborators.